Well, now we've gone to digital broadcasting using the same transmitter towers, such as the Empire State Building, or in San Francisco, for which I have the data because I happen to be close to it. In this tower, which is known as the Sutro Tower, it's taller than the Washington Monument. It has 31 TV transmitters on it that serves the entire San Francisco Bay Area. They're all up here, high above this thing. And what's happened with the Sutro Tower? This is just an example of what our transition to digital television has done. On the left here are the old transmitters that were on that station, not all of them. These are the powerful ones. There were VHF, very high frequency stations, well, with fairly low power transmitters of order hundreds of kilowatts. But here were the UHF stations, like 3,000 kilowatts. That's a 3 megawatt. Here's a 1 megawatt. Here's a 5 megawatt station. There's another 5 megawatt station. 3.5 megawatt station. Total power electric of 18 megawatts going out. This is a tremendous amount of power. All of it was going into space because it's radiated out horizontally so it'll reach people's antennas. These are, it says future because this slide is a few months old. These are the stations that are presently transmitting on that station. The VHF stations are all gone. The FM stations don't count. These are not TV stations. Their powers are very slight. But look at what's happened to the TV stations. No longer do we have 5 megawatt stations. We now have a few that are 1 megawatt, but most of them are only a few hundred kilowatts. That's all it takes to deliver a useful signal to people's houses. The total power has gone from 18 down to 5 megawatts. Earth is getting fainter. Well, that's not the end, because what's also happening on Earth is that other ways have been invented to deliver television to people's houses. One is cable television. That's really bad news for us. We lament that every night because cable television doesn't release any power into space. But something else is a technique which is an extremely powerful one, which is this is out of place. This reminds us that we also are reducing our power levels because we have to share radio frequencies as we do in cell phones. But the other thing that is, I think, really the wave of the future, even more than cable television, is direct-to-home transmission of TV. This is a picture of the Galaxy 11 spacecraft, which transmits many, many television channels on either DirecTV or Dish Network to people's homes, to 18-inch dishes that you find on their houses. It's probably one of the best ways to get television here in Greenbank. I haven't checked with any of my friends here to see how prevalent this is, but it's an extremely good system. Spacecraft is about 10 meters across, about 30 feet across. It has a number of antennas because it transmits television specifically to the United States, very carefully engineered so that the radiation falls just on the United States, but also to South America and to Mexico. And here's the radiation levels of this spacecraft. And just look at this one here. The KU band is the band which carries the TV stations to people's houses. And the power output is 75 watts or 140 watts. No longer a million watts. 75 watts, about the same as a light bulb. And not only that, it's all focused on the Earth. And this shows the radiation patterns, as they're called, where the power is delivered. As you can see, the engineers have been extremely clever, much to our horror, in making it so that all the power is developed where the people are. People who paid for the reception. They even have a finger that goes out to Hawaii. They have a finger that goes out to Puerto Rico. This is the American beam. As I said, it's also got a Brazilian beam on it and a Mexican beam, which aren't shown in this diagram. Well, all this power falls on the surface of the Earth, and a little bit is reflected. But out of the 75 watts projected on the Earth, perhaps 5 watts is reflected into space. So what used to be 1,000,000 watts or 2,000,000 watts is now 5 watts. It's not much more power than a cell phone. It's going off into space. And so the Earth is becoming quickly very hard to find. And of course the message there is that if other civilizations adopt this technology, which is an extremely good one because it can serve any place, rural areas, very isolated places, reliably at low cost, affordable cost, planets get very hard to find. What this says is our search is going to be much more arduous, may take a much longer time, and we just have to face that reality and devise systems which can detect signals such as this. Now, of course, we have great instruments. GBT. GBT, by the way, is potentially the most powerful instrument in the world for searching for signals near the center of our galaxy. The Arecibo telescope is larger, 300 meters, but it cannot look at the center of the Milky Way because of its construction. It can only look to the equator and to the north of the equator. The largest in the world that can look to where the stars are, which is where we should look. Now we realize we have to look at all the stars and the space in between them. The only thing that can do that well at the heart of our galaxy, where most of the stars are, is the GBT. It isn't doing it yet, but we hope somehow to make that possible. And now there's another instrument being built which will add to our observing power. This is an instrument being built by the Chinese called FAST, which stands for 500-meter astronomical spherical telescope. It is modeled on the Arecibo telescope, except it has 6 towers, and the reflector, instead of being 300 meters, is 500 meters across. It's a very sophisticated system in that they will have mechanisms which adjust the antenna to the dish so as to point the beam of the telescope in different directions. And it will also move the energy collectors using winches and long cables so as to aid the telescope in different places in the sky. A very challenging, very expensive, very difficult technological experiment, but it is now underway being built. And one of the things it will do is SETI. Well, this may be a big help. One of our other hopes is that we might go to the back side of the moon, the far side of the moon, and build perhaps things like the Arecibo telescope and craters there. It turns out because of the lower gravity on the moon and the lack of wind, that you can build a duplicate of the Arecibo telescope that's 50 kilometers across. And this is a crater that's about that, of that size, using ordinary iron and steel. Of course, that doesn't exist on the moon, but it can be mined there. But that will require, of course, a tremendous development of technology and metallurgy and steel mills and all of that. But the good side about the far side of the moon is that it's the only place in the whole solar system that never has the Earth in its sky, and therefore never receives the radio interference from Earth, which is the bane of SETI observers. So that's why it's the ideal place in the solar system. Of course, in addition, there's the advantage of the low gravity allowing you to build very large instruments with normal materials. One other dream we have is that this will come true. This is a very strange slide, but it's a picture of something that was proposed many years ago, was considered, well, too expensive, but nowadays the economics have changed so that this might, in fact, be viable. And in fact, one such example is being designed for launch. But what is it? It's a solar power station in space. It has a large array of photocells which collect sunlight very efficiently because there's no atmosphere to absorb any of it. All of the electrical power so collected is transformed into microwaves and transmitted from systems down to a receiving system on the Earth, which has to be about 1 kilometer in diameter. One of these things could transmit as much power as about 10 ordinary electric power stations. Very expensive, but yet the claim is being made that it's actually cost-effective to produce electrical power this way. Would, of course, take hundreds of these, perhaps thousands, to supply all our energy needs. But to SETI, the good thing about these is that when you transmit the power down to Earth, not all of it is captured. Every receiving antenna is imperfect enough to reflect some into space. The typical power being sent to the Earth is 1 billion watts in each beam. About 1 or 2% will be reflected. Well, what's 2%? That's about 20 million watts. So once again, we've got a 20 million watt signal going off into space to be detected by another civilization. So if this is what other civilizations do, it's the solution to our problem. After all, they will be detectable, but we will need to look for signals like this. Now, I want to mention one other possibility because I promised to tell you about the long future. And this is a way by which we could attain incredible sensitivity for detecting signals in the not so distant future, within the foreseeable future. It's a system which is available to us. It's available to every civilization because they all have a star, except the rogue planets don't have a star. But for all of what we'll call the normal civilizations, they have a star. Our star is the sun. And what we know, both from the general theory of relativity, but also from actual experiments, is that the presence of a large mass, such as in a star, actually bends space. It doesn't refract in the normal sense of a lens refracting. It actually bends space so that anything traveling in what it thinks is a straight line travels along a curved path. And the closer it is to the mass, the more the bending is. And what this does is cause light to travel on paths. I shouldn't say not light to be bent, because it isn't bent. It's traveling along paths which themselves are bent by the gravity field, bent so that they focus just the way a lens does. And so somewhere way out here, there is a focus. It turns out for the sun, it is at the rays that are most deflected are those that pass right by the edge of the sun. They're focused at a distance of 550 astronomical units from the sun. But what's the astronomical unit? That's the distance from the Earth to the sun. So this is about 10 times the distance to Pluto. Way, way out, farther than any of our spacecraft have ever been. Our most distant spacecraft now are about 120 astronomical units from the Earth, and they've been traveling for 30 years. So this is another four times larger distance. The rays that pass not so close to the star are focused at more distant points of the power. But the result of this is to create an enormously powerful lens. Its diameter is more than 1 million miles in diameter. It gives it a resolution, a sharpness of image, which is about 100,000 times greater than we look at with any telescope in the vicinity of the Earth, any of the ones we're building on mountaintops. 100,000 times. Its collecting area is the energy that comes to you at any given place from a ring, a narrow ring at the right distance from the star. But the area of that ring is typically radio wavelengths equivalent to the collecting area of 30,000 Arecibo telescopes. So what you get out of this is suddenly something that is 10 to 100,000 times more sensitive than we can ever build on Earth. And it has a resolution 100,000 times greater. You can not only detect planetary systems, you can detect actual planets, and you can resolve them. You can see details on planets 100 light years away with one of these lenses. And so we envision this. Here's the observer, here's a distant source. This could be a radio transmitter, it could be a planet. The radiation comes, is deflected through the bending of space around the star. And there's this ring, which is called the Einstein ring, from which light comes to the observer. This then is an extremely powerful system. There's one hitch, of course. You all already seen what it is. You've got to get to 550 astronomical units from the star. And in fact, you have to go a little farther than that because the rays that graze the star get distorted by the atmosphere of the star itself. So you really have to be about 600 astronomical units from the star. But it is a super powerful system which should easily detect even the faint television signals of very distant worlds. You can resolve planets. You can see, in fact, the lights of cities at night with this. And once you realize how powerful it is, you get it in your head that this is what all civilizations will do eventually as their space technology becomes adequate. The big trick is to get out the 600 astronomical units or something. That really takes a nuclear-powered rocket engine. Some of those are being developed. It's probably 100 years away for us, but 100 years from now, we could actually be doing this. And that means other civilizations not only can be doing it, but they maybe have been doing it for hundreds or thousands of years. And in fact, most of the technical civilizations will probably be at this stage. And so we should take this into account when we design our search methods. It's beautiful for communication if you use the star at both ends, which you can do, or you can use a second star. It turns out you can communicate with very low power levels if you use the gravitational lens as a communication link. And so what this has said to me is that right now this is very outside our capabilities. But we know what's required, and there's no physical limitation to building the technology that can produce the necessary hardware to do this thing. And if we can do it, other civilizations will have done it because it is such a powerful way to learn of other worlds and to communicate. And this gives us hope again that SETI will succeed. When we do, we may find that what you're seeing here is widespread in the galaxy. There's, if you will, a galactic internet, which consists of the countless examples of the use of stars as gravitational lenses. And this way, so the whole galaxy is interconnected, just like in the internet. And that would be a wonderful thing to discover. So there's hope. It's very tantalizing. And I think I will stop there. Sure, I will be glad to take questions. Yes.
Well, what do you think the chances are that we have been detected by other civilizations?
There is a real chance. As I said, the signs of our existence, the ones that are detectable by fairly ordinary systems, have been radiated in space for 50 years now. And I haven't done the calculation recently, but there's about 2,000 stars that are receiving those signals. Now, in 2,000 stars, there's some chance, not a big chance, that there's a searching civilization there, so there's a chance. On the other hand, if they're using gravitational lenses, they can detect farmland in cities and such. And so they could have learned of our existence perhaps hundreds of years ago. And not only that, well, it's again, many, many more stars, because if they can detect us from a distance of 1,000 light years, say, it's all the stars within 1,000 light years become possible detectors of our existence. So it's an interesting question. How often does the gravitational lens be exploited? If it's common, it's used, then we probably were detected long ago. And that's kind of a fascinating possibility.
Have you added any parameters to the Drake equation?
Have I added any parameters to the Drake equation? You know, the old parameters, there's 7 of them. Out here there are several exhibits. And I know some of you are going on a tour of Pocahontas County to get your books stamped, learn about all those parameters. The 7 parameters have sufficed for 50 years now. They have, in a way, been altered to be more more generous in what's included. For instance, sometimes people very commonly write me and say you should have a parameter for politicians. How does the presence of politics influence the number of detectable civilizations? Well, there is a point there. That is important, but it can be subsumed into existing parameters. So the 7 parameters seem to encompass all the effects we know of that influence the number of detectable civilizations. So far, no adaptations, alterations, or alternative versions are required.
That's good for 50 years.
Yeah, I'm proud. Let's, lady there.
Would it be true then that the very early TV programs would be being broadcast into far
Yes.
reaches as opposed to present TV?
Yeah, the present TV hasn't gone very far. Any TV that's been broadcast in the last 4 years has not gotten to any star yet. But the earliest TV has gotten to all 2000s. So there are a whole bunch of stars that have just seen Super Bowl I and are really getting excited. Hey, we got something to watch now that we didn't have before. It's 2,000 stars that maybe see Super Bowl I, but only 1,500 have seen Super Bowl III. Maybe I Love Lucy is a very popular program, thousands of stars, but not on any near, not on any. On thousands of stars, including nearby stars. But the nearby stars saw that, 20, 30 years ago. This is the ones that just received it. I Love Lucy, Howdy Doody. It's out there.
If we assume the likelihood of gravitational lenses and then stop to think that we've equipped nearly, I think it's 3 billion people with cell phones now, need we worry about the lack of television transmitters as beacons?
TV stations are still much more brilliant than cell phones. Now, I think maybe you're asking, is all the power is transmitted from cell phones a detectable signal?
In aggregate, yeah.
I had that same thought and made the calculation. Turns out it isn't, because the cell phone radiation is spread over a broad bandwidth. And if you work it out, 3 billion cell phones, but most of them are in action only a small fraction of the time. How much of the time do you use your cell phone? If you take that into account, probably 1% of them are actually transmitting at any given time, so it's a much smaller number. But they are transmitting on many different frequencies. So the aggregate of cell phones does not equal the aggregate of television.
Should a new beacon initiative be part of SETI then?
Yes, as long as we don't have to pay for it. Well, there's an argument in the SETI committee which is interesting, which is it's been recognized if they make beacons for the benefit of others, don't we have an ethical requirement to transmit also? Isn't that fair? Isn't that the proper thing to do? And it gets to an interesting philosophical problem. It has to do with, is there altruism in the universe? Do civilizations do something for the benefit of others that are of no benefit to themselves? If that is the case, we should do that also, because that would be the ethical thing to do. But transmitting costs a lot. And I think the counter-argument is sort of the one I've been giving, which is the Earth is also already transmitting a lot of detectable stuff. So that almost anything we can transmit would just be frosting on what's already a very big cake. But it's interesting, a very active discussion. There are actually international meetings on this subject of should we be transmitting? Is it an ethical requirement that we do this to be a moral situation, a moral civilization?
Is there any interface between the work that you do and your colleagues do and ufologists?
No, we do not. all of us, not all of us, many of us have interacted with ufologists and found it very disappointing. And I include myself in that number. I've actually published some papers on it. And what we have found is that when you actually dig into UFO reports, at least the ones I've dug into, and they're all the people I know have dug into, everything always falls apart. And it gets back to a statement that was made by Carl Sagan years ago, which is that the claim that some event is the result of an interstellar contact or mission to Earth is a very grand claim, and grand claims require grand evidence. But what's grand evidence? It's an artifact, an object, or that's clearly not of this Earth, or a fact delivered to us somehow to an abductee or one of those people, which we can go out and verify to be true. In fact, we didn't know, but can verify to be true. And in all the history of UFOs, that has never happened. There's never been an artifact. And so we're saying, in essence, case not proven, we'll wait for an artifact to be delivered and then we'll take it seriously. Now, as I said, there's very strong arguments against interstellar direct contact with tremendous energy requirements. There's some other problems I didn't mention for lack of time, but you can't really go as fast as I said, because if you hit a pebble, the energy release is more than that in a nuclear bomb, and the mission is canceled. So there's some other problems with all of that. But we do not interact with them because the history has been that it's not fruitful.
Yes, sir. Dr. Drake, you and I are of the age where we go back, let's say 1962. I was just wondering if you ever remember a series called The Outer Limits.
Yes.
And the first one they showed was called The Galaxy Beam. It was about a radio engineer on Earth who was sending waves into space, and he contacted another being. And I just wonder if you remember that.
I don't remember that episode.
It's all-
Sounds like though I should have.
I'd like to make a comment. I wish your telescope operator.
Oh, that's Fred Cruz. The light stood in my eye, so I couldn't see it.
These were all the guys that thought we were the guys that did the work. I remember I was set up with 85-1 with that equipment that you were talking about. We had all sorts of monitors. We had things like chart recorders, we had things like bing, 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 sounds, and all sorts of things like that. If anything came up, that came in on the telescope beam, we would get the record. Well, a gentleman by the name of, what was it, Norwegian,
Hey, Bottom.
Dave Bottom.
Yeah.
He was here in this country at that time. He's one of our chief engineers. And he had bought a new car that just came out, the first car I knew of, that had an engine in the rear.
Corvair.
He pulled up in front of the doors, big windows in the side of the 85-1 control center building, and we all ran out there to see this car. When we came back in, all the chart recorders had been boomed and banged and everything else. There was nobody there to get it.
But what do you suppose that was? Corvairs, I guess, did that. That's why we have diesel cars here now. Yeah, Fred was the chief telescope operator. He spent many, many days punching buttons to make everything happen. Because I didn't do all the observing. In fact, the telescope operators did most of the observing in Project Osmo.
He had names for the astronomers. Aviation, who was the director, we called him DSH. We called you Foxy Dog Dog.
I never knew that.
Other questions for Dr. Grace?
Dr. Drake, I was wondering about this gravitational lens. much the light rays bend around the sun. It depends on the mass of the sun, that's correct? The heavier the mass, the more it bends. I guess the moon would be too light.
The moon is too light.
It'd be too light.
The moon is too light. The more massive stars do more bending. And some forms of stars, such as the white dwarf stars, well, the bending depends on both the mass and how close the ray path comes to the center of the star. So if you have a compact star, such as a white dwarf or a neutron star, the path of the light becomes very close to much closer to the center of the star than with a normal star like the sun. And then the focal point is only 1 astronomical unit. If the sun were one of those kind of stars, we could be doing this today. Unfortunately, well, I guess fortunately, the sun's not that kind of star. The only way you make those kind of stars is with some violent event happening. But what you're saying is correct.
Since it takes light, like many thousands of years to reach certain stars in the galaxy, how does that affect our potential search for civilizations and contact?
It doesn't affect the possibility of succeeding. It just means that when you receive the signal, it's old. You're learning of a civilization, not as it is today, but perhaps hundreds of thousands of years ago. And some people, actually one senator, understood this and acted to cut off all funding for SETI because he said, well, I realize that if they succeed, they're going to be learning things from people before Columbus, and what can we learn from them that's useful? I'm glad people are laughing. It's obviously an idiotic statement because, yes, the signal may be hundreds of years old, but it may come from a civilization that's millions of years ahead of us. And this has been described as, very nicely, as SETI, when it succeeds, will become, this can be called the archaeology of our future. We will not be seeing what happened in the past, we will be seeing what could happen to us in the future.
I think that's a wonderful note to end on. Thank you.